Let's talk about something that seems super simple, but is actually a huge question. How do we agree on the size of anything? It turns out there's this one single, really elegant idea that solves it. And this idea is so powerful. It's used for everything from designing video game worlds to calculating shipping costs, and yeah, even measuring the entire universe. So let's break it down.
I mean, think about it for a second. An object looks huge when you're right up next to it, but tiny when you're far away. The shape can even look different depending on your angle. So what's its true size? How can we possibly find one stable, reliable measurement that you, me, and everyone else can agree on?
And that right there is what we can call the sizing up problem. To measure anything consistently, we need a system that isn't fooled by our changing perspective or an object's weird, unique, complex shape. And the key, as you're about to see, is to simplify a lot.
And the solution is just beautifully simple. We just ignore the complicated shape of the object itself. Instead, we imagine the absolute smallest, tightest fitting box it could possibly squeeze into. This is called a bounding box, and it is the master key to unlocking how we measure pretty much everything. Now, to really grasp how powerful this whole bounding box idea is, let's strip everything back to the absolute basics. We're going to start with the simplest case you can possibly imagine, a single dimension, just a straight line. The measurement of that one single dimension is simply its length. And for us to agree on any measurement, we have to have a shared standard, right? Well, for length, our standard is the meter. You're going to want to remember that because every other measurement of size we talk about is built on this one single idea. Okay, so we've got our one-dimensional unit locked down. Now let's build on it. What happens when we add a second dimension? Let's step into the world of flat objects, the plane, and see how our humble little meter lets us measure a whole new world.
And the process here is super practical. You can do this with anything. Take any flat object, a leaf, your phone, whatever. First, you draw the smallest possible rectangle that can fit around it. That's its 2D bounding box. Then, you just measure the two sides, its width and its height. That's it. You're done.
And that number you get from that super simple process, well, it has a name we're all familiar with, area. It's the size of that 2D surface, and you find it just by multiplying those two length dimensions you measured from its bounding box, the width times the height.
And this is where it gets really cool, because you can see how our units just build on each other. Since we measured a meter in one direction and then multiplied it by a meter in another direction, our new unit for area is meter times meter, which we write as meters squared. That little 2 up top, it's powerful. It's telling you, hey, we're talking about 2 dimensions here.
All right, we've mastered 1 dimension, we've mastered 2 dimensions. Now for the final step, the one that really matters, applying this same exact logic to the 3-dimensional world that we all live in. Let's add that 3rd dimension.
You seeing the pattern here? It's the same elegant logic, just with one extra step. You take any 3D object, a book, a ball, an entire building. You mentally stick it inside the smallest possible box, its 3D bounding box. Then, you just measure the 3 sides, the width, the height, and now the depth. And the result of multiplying those 3 lengths is what we call volume. It's the total amount of 3D space that the object's bounding box takes up. So the really crucial point here is that we're still just measuring length. We're just doing it in 3 different directions and then multiplying them all together.
And you guessed it, the pattern holds up perfectly. The unit for volume is meter times meter times meter, or meters cubed. And again, that little 3 tells you everything you need to know. We are measuring in 3 dimensions. We've gone from the meter to the square meter to the cubic meter, all from one simple idea.
Now this quote points to a really neat mathematical shortcut. See, when scientists are dealing with massive numbers, they often use this tool called logarithms. And what's so amazing about them is that they turn the complicated act of multiplying these 3 lengths into simple addition. It's a hack that makes this whole system incredibly powerful for really complex stuff.
Okay, but wait a minute. I know what you're thinking. If you put a round ball into a square box, there's always going to be some empty space in the corners, right? The bounding box is, by its very nature, always going to be a little bit bigger than the thing inside. So how do we account for that? Well, that's where these shape factors come in. They're basically just little correction numbers, they're always negative, and they account for all that empty space that different shapes leave behind. A sphere fills its box a lot less efficiently than a perfect cube does.
Now, you do not need to memorize this table. It's just here to show you how scientists and engineers get that extra bit of precision when they really need it. But let's be totally clear. For everyday use, for understanding the big picture, this is the fine print. The key life skill here, the thing you want to walk away with, is understanding the core concept of the bounding box itself. That powerful, simple idea is what gets you 99% of the way there. So let's put it all together, shall we? We started with a pretty simple problem. How do you measure a weird-shaped object from different angles? And we found this one powerful idea that works for absolutely everything, from a straight line to a giant skyscraper.
So what are the big takeaways here? First, we use a bounding box to ignore complicated shapes and make things simple. Second, area, or meters squared, just comes from multiplying two lengths. Third, volume, meters cubed, comes from multiplying three lengths. And maybe the most important point of all, every single measurement of size we have comes from that one fundamental unit, the meter. And that little number at the top tells you exactly how many dimensions you're dealing with.
And there you have it. We live in a three-dimensional space, and now you understand the fundamental, totally logical system we came up with to measure any object inside of it, from a tiny line segment all the way up to, well, the entire universe in a box. It's a pretty satisfying system, isn't it? It all fits together so neatly. We've created these powerful new units for area and volume by multiplying our base unit, the meter. But that leads to a pretty fascinating next question, doesn't it? What happens when you do the exact opposite? What new kind of reality do you end up measuring when you start to divide a unit? We'll get into that next.